Welcome to this explainer. Look, today we're going to completely demystify artificial intelligence from the ground up. So whether you're trying to pivot your career, trying to absolutely ace an upcoming interview, or maybe you just want to finally understand what everyone is talking about, you are exactly in the right place. We're going to focus on how these systems actually work under the hood, not just what they are. The goal? To leave you fluent and 100% career ready.
Here's our roadmap for today. We'll unpack the AI hierarchy, look at AI as the broad umbrella, zoom into machine learning, dive even deeper into deep learning, and finally, we'll explore the wild frontier of generative AI. We're essentially using a Russian nesting doll approach here, systematically zooming in.
All right, let's jump right into Section 1, unpacking the AI hierarchy. We really need to clear up the biggest source of confusion right out of the gate.
Okay, so the absolute most crucial framework you need to grasp today is this. Artificial intelligence, machine learning, deep learning, and generative AI. They are not competing technologies. You don't just pick one over the other. Instead, think of them as Russian nesting dolls. They are nested subfields where each concept literally lives inside the one right above it. Just grasping this hierarchy alone is going to put you miles ahead of most people who just throw these terms around interchangeably.
So, moving to Section 2, AI, the broad umbrella. Let's go ahead and pop open that biggest nesting doll first.
What's actually really interesting about this definition is how it grounds the hype. Artificial intelligence is simply the science of building machines that can do things that normally require human intelligence. That's really it. It doesn't mean a machine is thinking like a human with consciousness or emotion. No way. It just means the machine was built to achieve a goal that a human would usually handle, like reading a document, spotting an obstacle, or making a decision. AI is just the overarching goal.
And you interact with this broad concept every single day. Think about it. When your email magically filters out a spam message, when Google Maps recalculates your route because of a traffic jam, or when Netflix somehow knows exactly what show you want to binge watch next, all of that is AI at work. It's totally seamlessly integrated into our daily lives.
But how did we actually build this stuff in the past? Well, historically, AI was purely rule-based and followed a super strict sequence. First, a human programmer would manually write out rigid rules, like if an email contains the words win a prize, then mark it as spam. Second, the computer just follows those rules exactly. Zero flexibility. But here's the problem, and it's a massive one. Step 3, the rules break. The real world is just incredibly messy and way too complex to hard-code every possible scenario. Spammers figure out they can just spell prize with a zero, and boom, suddenly your whole rigid system completely fails.
So here's a little insider career tip for you. Today, when people in the tech industry say AI engineer or AI developer, they almost never mean someone writing those old, rigid, rule-based programs. They mean someone who builds machine learning or deep learning systems. Just knowing the distinction between a hard-coded program and a modern learning model, that is going to immediately make you sound incredibly sharp in interviews.
And because the real world was way too complex for those rigid rules, researchers had to adapt. That brings us to Section 3, opening our next nesting doll, machine learning, the practical engine of AI. Machine learning completely flips the script. In the old rule-based system, humans write the rules, and the computer blindly follows them. But in machine learning, you give the computer examples, and it finds the patterns entirely on its own. Imagine trying to explain to a computer what a cat is by writing mathematical rules about exact ear angles and fur density. I mean, it's virtually impossible, right? With ML, you skip all that. You just show the computer 1,000 photos of cats and let it figure out the pattern itself. Examples go in, patterns come out. A real game changer.
Let's look at how this builds into an actual workflow, or what we call a pipeline. Building an ML engine happens step by step. First, you collect your data. Let's say 10,000 past house sales. Second, and this is absolutely critical, you split that data. You take 80% of it to train your model, but you hide the remaining 20% to test it later. Third, you train the model in this continuous loop where the algorithm makes a guess, checks the real answer, measures its error, and adjusts itself. Fourth, you evaluate its real-world performance using that hidden 20% to make sure it actually learns something useful. And finally, step 5, you deploy it into the real world.
Now, within this machine learning engine, there are 3 main approaches you really need to know. First up is supervised learning. This is where you provide labeled data, meaning both the input and the correct answer, so the system learns to map one to the other. Think of predicting house prices. Second is unsupervised learning. Here, you give it unlabeled data, and it basically has to find hidden groupings on its own, kind of like segmenting customers into different buckets. And third is reinforcement learning,
where an agent takes actions in an environment and learns through rewards and penalties. Honestly, it's literally just math's version of training a dog with treats.
It's definitely not foolproof, though. The absolute biggest pitfalls you've got to avoid here are overfitting and underfitting. Overfitting happens when your model simply memorizes the training data instead of actually learning the underlying pattern. It's exactly like a student cramming the exact questions for a practice test, but then completely bombing the final exam because the questions changed just a little bit. Underfitting is the exact opposite. The model is just way too simple. It's like studying for only 5 minutes. You simply haven't learned enough to pass anything.
Time for another quick career tip. If you want a job in this field, focus your energy deeply on mastering supervised learning first. I highly recommend starting your journey using the scikit-learn library for Python. Then, once you've got that down, move on to PyTorch. Also, a quick warning here, looking at simple accuracy metrics can be dangerously misleading if your data is imbalanced. Always dig deeper than just the top-level accuracy score.
All right, let's zoom in even further. We're opening our third nesting doll in Section 4, Deep Learning. This is the true powerhouse behind all those modern AI breakthroughs we constantly see in the news. So deep learning is a highly powerful type of machine learning that uses layered artificial neural networks. But what does that actually mean? Well, think about how you recognize a face. It happens in stages, right? First, your brain notices basic edges and curves, then it pieces together shapes like eyes and noses, and finally, it recognizes the full face. Deep learning mirrors this biological process exactly. It passes raw data through hidden layers of artificial neurons, with each layer processing increasingly complex and abstract features.
So, how do these networks actually learn all this? It's basically a 5-step cycle. Step 1 is the forward pass, where data flows through the network to make a prediction. Step 2, we calculate the error, which is often called the loss. Step 3 is where the real magic happens, backpropagation. The error signal is literally sent backward through the network, so each layer knows exactly how much it contributed to the mistake. Step 4 is gradient descent, where the network adjusts its internal weights. Just imagine a ball rolling downhill trying to find the absolute lowest point of error. In Step 5, you repeat this cycle millions and millions of times.
As you navigate this space, there are a few key architectures you absolutely need to know by name. CNNs, or convolutional neural networks, are your go-to for scanning images and detecting shapes. RNNs, or recurrent neural networks, are specifically designed for sequential data like text or audio because they actually have a memory of what came before. And finally, transformers. Transformers completely revolutionized AI by processing everything all at once, using a mechanism called attention, basically figuring out which words or data points matter most to each other. This right here is the architecture fueling the modern AI boom.
Now, if you're eyeing jobs in computer vision, natural language processing, or speech, pay really close attention to your tooling. PyTorch has become the dominant framework across research and industry. And here's a massive time saver for you. Modern developers rarely train these huge models from scratch anymore. Instead, the real skill you need is learning how to take existing, pre-trained models and fine-tune them for your specific needs. And that brings us to our final section, our smallest, newest, and undoubtedly most explosive nesting doll. Generative AI. Welcome to the absolute frontier.
We are currently experiencing a massive philosophical shift in technology. Think about it. Classic AI asks an analytical question. Is this a picture of a cat? But generative AI asks a fundamentally creative question. What would an entirely new cat picture look like? We've moved from simply analyzing and categorizing patterns in existing data to actually inventing entirely new content that has literally never existed before in the history of the world. It's wild.
The most famous examples of this are large language models like ChatGPT. But how do they actually pull this off? Well, first is pre-training. They read massive portions of the internet just to learn how human language works. Second is their core task, next word prediction. At the very heart, they are just incredibly good at guessing what the next word in a sequence should be. Third, they undergo fine-tuning using reinforcement learning from human feedback, which basically makes them safer and much more helpful to us. Finally, at inference, which is when you type a prompt, they generate text word by word based purely on statistical probabilities.
And beyond just text, there are other mind-blowing architectures out there. We use GANs, or generative adversarial networks, where two networks actually compete against each other. One creates fakes, and the other tries to spot them, which is exactly how we get hyper-realistic deepfakes. Then there are diffusion models, the tech behind tools like DALL-E and Midjourney.
They work almost like magic, learning to slowly reconstruct crisp, high-resolution images out of pure static noise.
However, this frontier is definitely not without some severe challenges. Because these models predict plausible text rather than retrieving verified truth, we face immense issues with hallucinations, which is when the AI confidently states completely false facts. We also have to grapple with baked-in bias, where the AI simply amplifies the prejudices already found in its human-created training data. Add to that the massive legal questions around copyright and the ownership of synthetic content, and it's a lot to navigate. Understanding all of this really leaves us with one incredibly important question to ponder. How are we going to safely govern the synthetic world we are so rapidly building? Thank you so much for joining me on this explainer. I really hope you're leaving today feeling a whole lot more career ready.